Yeah. So I think it's not resistivity. Sorry, my bad. Okay. So let us start. Sorry, this rho 1 and rho 2 are my current densities. Sorry, charge density on two different regions of a rod in which the current I is passing. Got it or not? An area of cross section is given as A. The question is find the charge on the common surface. Okay. So we completed all this. Now based on this, you can try to understand that we have one formula that basically look over here. We have one big formula that current density is simply I by area A or not. Yes. So we can use this term to understand or to solve this question that I know that current density is equal to, sorry, J is equal to current density is equal to I by area A. Is that fine? Now, basically that means that I can be written as J into A, isn't it? Now, if I know my density and if I know my current density, like look over here, you know the electric field formula. What is the formula? I think we have J is equal to sigma E or not. Yeah, so E is equal to what? Sigma J. And basically this sigma is called as what? Conductance. Are you able to get me or not? Sorry, 1 minute. I think J is equal to sigma I. Opposite. So look over here. J vector is equal to sigma E vector. Are you able to get me? E by sigma. Correct. So sigma into electric field E vector. Are you able to get me or not? Now look over here. If I find electric field, that means it is 1 by sigma into J. Are you able to get me or not? So basically, Baba, what I am doing? Okay, so this is not charge density. I was right before. It is still resistivity. Sorry, because I don't know what kind of, there is nothing written over here in this question. Okay. So look over here. So basically electric field is what? If I know that electric field is 1 by sigma into J. So you know that resistivity is 1 by sigma conductivity, isn't it? Are you able to get me or not? So that means that I can replace the E value. E is equal to what? Rho into J, where rho is representing my resistivity over here. Are you able to get me or not? Yes. Now, if the electric current is towards this side, that means that here some electric field E1 will move, and if resistivity is different, so here some another electric field will move or not, because it is dependent on resistivity. Are you able to get me or not? So then the flux through any reason means if I want to find the flux, so what will be the flux over here in this reason? Flux will be, it will be, what is the formula of flux? E dot ds, isn't it? So net flux will be what? Phi 2 minus phi 1, which is created by one electric field E2 because some of the charges are stopped. Got it or not? So final net flux is what? Final flux minus initial flux, because that much charge, basically you try to understand. It is asking find the charge on the common surface. Basically that charge will only be on the common surface which are stopped on the common surface, isn't it? So basically if in from this region the flux is phi 2 and from this region the flux is phi 1. So if I subtract phi 2 minus phi 1, I'll get the net number of flux which is stopped over here or not. So flux present on the surface. This is delta phi which is present on my surface, which is phi 2 minus phi 1. What is the formula of phi 2? E dot ds means E into area A, E2 into area A minus E1 into area A. So E2 is what? Rho 2 into J. Current density will remain same because area of cross section is same. So J into A minus rho 1 J into A. So basically J into A is I. Yeah, so it is I into resistivity rho 2 minus rho 1. That is my net flux which passes through the or which is present on that common surface. Are you able to get me or not? Into basically this is my net flux. Now basically net flux phi is equal to Q enclosed by epsilon naught or not. So charge present on that surface is I times epsilon naught rho 2 minus rho 1. Are you able to get me or not? Is that clear? Perfectly? Okay, so let us move on, or let us do one more last question of resistance, which is little bit difficult. Okay, it was not my plan to do it, but I thought why to leave that last question, isn't it? Although it takes some extra time. So we did the cylinder case, but we didn't did the elongated cylinder case. It says that, yeah. So we have this kind of a cylinder. 1 minute. Yeah, kind of a frustum. Correct. Okay. So this is a kind of a frustum I have, and it's saying, what it is saying that this conductor is of length L. The length of the conductor is L. Got it or not? And radius of the conductor is given. Both the cases, both the radiuses are given to us. One is A, another one is B. Got it? One is A, another one is B. Question is बोल रहा है कि the resistivity, let me write with B. Question is the resistivity of the conductor okay is given is rho. Are you able to get me or not? And radius of cross section is varying, increasing A to L. Consider, assuming B minus A to be less, too much less than length L. Okay. Find the resistance of conductor. Assuming B minus A to be too much less than L. Find the resistance of the conductor. Tell me how to do it. And it's a solid conductor, okay? Tell me. It's easy only. Don't take tension that it's too tough. Just it requires a logic. Okay. Apart from that, it does not require anything else. Yeah. Should I do? Okay, there are some things which you need to understand. See, first thing, here radius is increasing slowly, isn't it? So first thing, my radius is itself increasing. And it is a kind of a frustum. It is a what? Kind of a frustum. So I need to divide this into two more reason or not. First one, which is kind of a cylindrical reason. Are you able to get me or not? Basically, I can divide this into how many reasons? Two reasons. One reason in which it is a kind of a cylinder basically. Are you able to get me or not? So look over here. Let's suppose if here this angle is how much? Theta. Write it down. So this length will be also length, isn't it? And from here to here, let's suppose this length is A. Okay. And this length is, let us consider that this reason left out is, let us write Y, some length Y. Okay. That is better, isn't it? Is that clear or not? So similarly, I can have the another reason, but let's suppose if I calculate for this reason, I can multiply by 2 and I'll get the net answer or not. Yeah, basically I'll multiply by 2. Is that true? So look over here. What I'm doing is I'm considering a small ring, sorry, a small disc in that frustum which is located at a distance x from this center. Okay? Or let us consider it this way. Let us consider that this is located at some distance x, isn't it? So look over here. What will be the area of this? Basically, I can, if I can find dr, and it's, let us consider that its thickness is how much? Dx. This thickness is how much? Dx. Yeah. So what will be the area of this? Simple. Uh, dA will be how much? What will be area of this disk? Can you tell me? Basically, if you look over here, so its radius is how much? A plus y or not? Almost a plus y, isn't it? So pi, it will be pi a plus y whole square, isn't it? That's my area of the disk, isn't it? Which has some thickness dx. Are you able to get me or not? I'm just finding area. I'm not finding volume. Are you able to get me or not? If it would have been volume, I would have multiplied with dx. Are you able to get me? So therefore, a small dr for that will be what? Resistivity rho. Length is how much? Thickness, which on which the current is passing. I is passing like this. Why not? So rho into dx divided by area, which is pi a plus y ka whole square. Are you able to get me or not? Correct. So look over here. Basically, if I want to write this y in terms of tan theta, so I can write now tan theta is equal to y by x, which is this y by x squared or not? Okay. And that must be equal to, this theta is also for this bigger triangle or not? which is equal to b minus a by length L. Isn't it correct? So I can use the formula na, like if I want to write a in terms of let's suppose if I want to write here it is dx, so I should write y in terms of x or not. So y is equal to what? X tan. So put it over here. Dr is equal to rho dx by pi a plus x tan theta ka whole square. Are you able to get me or not? So my idea is very simple that when I got this figure, I had to find the resistance. Now here resistivity is also constant, but resistance is slowly increasing in terms of cross-sectional area, but not in terms of length. Are you able to get me or not? So I took such a material, such a particular cross-sectional region on which the area was small and for which I founded my dr. Now I can integrate from this side till this side such as to get the net area, net resistance or not. So this is my idea. Got it or not? Which can be done with the help of tan theta. Okay. So look over here. I got my dr. I got dr as rho dx by. So let's suppose if I want to find now R effective. So R effective will be what? Simple integration rho by pi outside dx by a plus x tan theta ka whole square. Isn't it? Are you able to get me or not? So, do you know this form? What is the integration form of this? So, it is like a plus x tan theta can be treated as u, but it is of no use because tan theta is also constant term, isn't it? So, I can write R effective as simple rho by pi. This is 2 minus 2, I can write it. So, a plus x tan theta to the power of minus 2 plus 1 divided by minus 2 plus 1 into divided by the coefficient which is multiplied with variable which is tan theta, isn't it? And this integration will vary from somewhere to some region. So this look over here, x is from where to where? 0 to length L or not? So the integration must be taken from 0 to length L. Is that clear or not? Are you able to get? So what I will get? I'll get as minus of rho by pi ax tan theta means 1 by tan theta into 1 by a plus x tan theta. This is my whole relation. And that varies from 0 to length L. Is that clear? आ रही बात समझ में? So I got this equation, isn't it? I got my equation, I got my R effective relation. So can I just replace L over here? So the equation will become R effective will become take minus of rho by pi tan theta common. Let me solve it over here. So R effective is equal to minus of rho by pi tan theta common, and this will be 1 by a plus L tan theta minus 1 by a. Is this is going to be my term? Yes, that's correct or not? I'll not get any other terms, na? Yeah. So look over here. What is the value of tan theta now? Tan theta is b minus a by a all now. Yes. So replace it. R effective is, yeah. So here also I can replace pi b minus a into length L and 1 by a plus b minus a minus 1 by a. Are you able to get me or not? So this a got cancelled and I'll get the answer as rho L by absorbing the negative pi B minus A curly bracket 1 by A minus 1 by B. This is the formula for R effective. Is that clear? It can be also further simplified. R effective equal to, I can take the LCM. This will be rho L by pi B minus A into, yeah, B minus A by AB. This also got cancelled. And R effective is ultimately rho L by pi AB. Are you able to get me on? Is that clear? Basically, you should remember for this, for area of a frustum, curved section area of the frustum is given as pi into A into B. Are you able to get me or not? And that is, yeah, we can just use the simplest form, such as to get the answer. Got it? Is it perfectly clear? Okay, write it, then I'll move ahead. Okay, 1 minute now. So we got to know how the resistances are present, how the things are there. But one point is very, very important to understand, that these resistances which we are understanding, or these resistivities which we are understanding, basically they are dependent on temperature also. Yeah. Dependent on temperature. I think I'm writing the correct spelling now. Okay. So resistivity means, many people think that resistivity does not depend on temperature, but that also depends. Are you able to get me or not? Resistivity depends. Our resistance also depends. Are you able to get me or not? Yes. So let us understand how it depends. First point, I'll give the direct formula that resistivity depends on my temperature as is equal to rho naught e to the power of alpha delta t. How it is depending? E to the power of alpha delta t, where alpha is called as thermal coefficient. You know that thermal coefficient of resistivity. T. Delta T is my change in temperature. T minus T naught it is, which is also called as temperature difference, isn't it? Then you know rho naught resistivity, it is the resistivity at temperature T naught, and rho is my resistivity at temperature T. Are you able to get me or not? So this is my variation of resistivity. Now the point is very, very simple, that as alpha delta t means alpha is very, very small and delta t is also very, very small, because alpha is always very, very small, right or not? It is almost 10 to the power of minus 5 or something like that. So basically they are very, very small than 1 even. Are you able to get me or not? So this is why resistivity formula is given as rho is equal to rho naught 1 plus alpha delta t. इसका मतलब क्या है? Given my resistivity is dependent on temperature. For higher temperature, it is exponentially dependent. For lower temperature, it is linearly dependent. Are you able to get me or not? Yes. Less than 1000 degrees centigrade. Now, as R is equal to rho L by A, so if I'm not changing length and area, so basically I can replace rho as RA by L, which A and L will cancel, and this will be given as formula R is equal to R naught 1 plus alpha delta t. Is that clear or not? Now, you can ask me, sir, how did you got this formula? What is your real imagination? How it has came? What is the actual nature of these? So we will talk about that. But this is my formula based dependency. First we'll understand the formula and then we will move ahead. Are you able to get me or not? So look over here. The question arises, what is this R naught and T naught? Remember that there is a reference of this R naught. My R naught is taken specifically. R naught is defined at 0 degree centigrade. Where R naught is defined? Yeah. So this means that T naught must be equal to how much? 0 degree centigrade or 273 Kelvin. You should always start your calculation from 0 degree centigrade whenever you are going to find the resistivity of the given question. Are you able to get me or not? Is that clear? Ha ha ha. Yeah, you have to always use for 0 degree centigrade. The reference is set. Got it? So look over here. Let us understand what is the real meaning of this. What is happening. We'll try to understand. Is that clear or not? Okay. So look, try to let us understand. Let us understand the physical meaning of dependence on temperature. Now look over here. Let us understand first thing. Acha, let's suppose if in any conductor the temperature is decreased. What is decreased? What will happen after that? If temperature is decreased, tell me. Can we say that randomness, yeah, randomness of electron decreases, isn't it? Achha, if randomness will decrease, then what will happen after that? What will happen after that? Basically, when randomness decreases, does the collision among the electrons also decreases? What will happen? The collision among the electrons will also decrease. Achha, if collision decreases, does my relaxation time increases or not? Yes. So if collision decreases, what increases? Relaxation time increases. If relaxation time increases, does my drift velocity increases? Because we know that relaxation time is that relaxation time in which the electron after the collision starts to gain that velocity, isn't it? So during that process, if relaxation time, if collision will decrease, the relaxation time, now the electron will collide over here. So relaxation time will increase or not? If relaxation time will increase, the increase in velocity will be very, very much. Are you able to get me or not? Now, as you know, the drift velocity increases. What decreases? Look over here. Do we have the relation of density, resistivity with our relaxation time relation or not? Isn't it? Look over here. If I think of resistance, sigma, what is sigma? Sigma is Ne mu, isn't it? कुछ तो बोलो हाँ या ना? So basically, if my tau increases, what increases? Simply, if my tau or drift velocity increases, mobility increases or not? Correct? Isn't it? So the point is very, very simple that if drift velocity increases, my mobility increases, isn't it? And if mobility increases, what increases? Conductivity increases. Conductivity increases, and as conductivity increases, resistivity decreases. But this is only happening for our conductors or metals. Only conductors or metals. Are you able to get me or not? Is that clear or not? So this is how what happens when then the temperature is reduced, when the temperature is decreased in the particular case. Are you able to get me or not? So these are my relations, isn't it? Are you able to get me or not? So basically, the reason for this is very, very simple, that here tau plays a very important time, means relaxation time is very, very necessary to understand, isn't it? Are you able to get me or not? And next thing is my drift velocity, which depends on my mobility, mu into electric field E. यही होता है ना formula? Let us check it. I think drift velocity is I think mu into E. Yes, isn't it? So look over here. We have so many good relations to understand in one book, that how the important cases are defined for all the cases. Now that means that somewhere this conduct resistivity depends on my relaxation time, isn't it? So this is not in your syllabus. This is basically for CBSE or JEE Mains. Its derivation is given in NCERT. Got it or not? So it says that the resistivity relates with our relaxation time as mass of electron divided by n E square tau. So basically, where n is my what? Number of electrons per unit volume. Yes. Are you able to get me or not? M is mass of electron. You can prove it using the help of that. Means I know Vd is equal to mu into E, and then there is a relation of tau with respect to Vd or not. So you can prove it, right or not? You can use that formula, and or you can use sigma is equal to any mu, that formula, that is also correct. And tau is my relaxation time, which is also known as average time interval between the collisions. Are you able to get me or not? So look over here. Let us talk. Let us have understanding. So first case, as we know, for conductors, take. Let us have a conclusion. Now we got to know that for conductors, as the temperature will increase, what will decrease? Relaxation time will decrease or not? Because due to more randomness. Yes. So for conductors, basically, when temperature increases, what happens? First thing, n remains constant, means my free electron remains constant. It does not change. Are you able to get me or not? So look over here, for conductors, as n remains constant, if you increase the temperature, what happens? Basically, You know that relaxation time decreases as more randomness is present. Are you able to get me or not? So first thing is n remains means our number of charge carriers remains constant, but our tau decreases means our relaxation time decreases very, it goes very down, means more collision starts to occur, and as my tau decreases, you know that resistivity will increase, isn't it? And if resistivity is increasing, you can relate here that alpha will be positive or not. So this implies alpha is basically positive. Are you able to get me or not? So we can say in a simple term that for conductors, resistance increases with increase in temperature. Is that clear? Hmm. Okay. Second case is for our semiconductors, isn't it? For semiconductors or insulators. Hold on. So when I consider semiconductors and when my temperature increases, what happens basically? When your temperature is going to increase, what will happen? Simple things will happen. First thing, number of free electrons will increase or not. Now, if free electrons have been increased, what happens? That it is experimentally found that randomness now is not more because of free electrons. See, initially, if acha, try to understand that if there is no collision, then there is no current basically. Are you able to get me or not? So, like just listen. Remember that you only say me. See, if this is a conducting body, and here I have some electrons. Now, if I provide the potential, what happened? That this electron started, but here was some atom. Well done. So this electron collided with atom and it stopped over here, isn't it? Similarly, there is another atom. This electron also collided and stopped over here. So if it stops, does the electricity will flow? No. This is the real reason of our insulators and semiconductors. That, see, just like we have friction, without the friction we can't walk, but if friction is more, I can barely walk. So friction is necessary also and evil also, isn't it? Are you able to get me or not? This is what they are trying to make you understand, that basically in conductors number of free electrons are very less in semiconductors and insulator. So what happens that since there is a scarcity of electrons, the electrons cannot interact with other electrons easily. Are you able to get me or not? So due to that, although if we provide this potential, electron starts to move, but it is blocked by the other atoms, not the electrons. Are you able to get me or not? And if this electron does not collided with this electron, then it will never ever pass the electricity. Are you able to get me or not? So when I am increasing the temperature from this atom, what happens? Suddenly one more electron is created. Now this electron can collide with this electron easily or not. And then, Baba, simple. If I increase the temperature, the atom will lose one electron or not. Ah, so if I increase the temperature, the vibration increases and more number of free electrons are generated. That is why I am writing as temperature increases, free electrons increases. So when free electron has appeared over here, this electron will collide to this electron, and they will collide such as collisions will start happening. And as these collisions started to happening, the material will start conducting the electricity further or not. So this is what they are trying to say, that initially my relaxation time was 0. Initially my relaxation time was what? 0, because there were no electrons which were colliding with each other. But now, as free electrons are more, some relaxation time is present. Are you able to get me or not? So that's what they are saying, that experimentally it is found that as temperature increases, number of electrons multiplied with their relaxation time basically increases. Are you able to get me or not? So when this increases, this means that resistivity will decrease as the temperature increases in semiconductors and insulators. Are you able to get me or not? So this implies alpha is basically what? Negative. Or you can say for insulators, what I'm writing, insulators slash semiconductors, as the temperature increases, resistance decreases. So this was all about your temperature dependency of our resistivity and resistance of the material on the temperature. Is that clear or not? Yeah. So let us do some question based on this. Write one question. बोल रहा है at 50 degrees centigrade the value of R is 100 ohms. Okay. Find the value of R at 100 degrees centigrade for a conductor having alpha is equal to 2 into 10 to the power of minus 2 per degree centigrade. Do it. You are getting how much? 100 and 102. How come? 100 and how much? No. This is where the people they think that this question is very easy. It's an easy question also. I'll tell you what the people will do. They will write R is equal to R naught 1 plus alpha delta t. They will put it R निकालना है. R naught is given 100. 1 plus alpha is 2 into 10 to the power of minus 2. And delta t 100 minus 50 is just 50 because it is degree centigrade, so no need to convert into Kelvins. Are you able to get me? So basically, this means that it is 100 into 1 plus 1, which is equal to 200 ohms. But this is a totally incorrect answer. This is a total incorrect answer. The reason for this is because already I told you that in this equation, it is measured, it must be taken always from the reference point. Are you able to get me or not? Here, you defined your reference point to be 50 degrees centigrade, then only 100 minus 50 is 50 now. So this is incorrect because your reference should be what? 0, not 50. So how to solve that? So first, let us define that what is my, because I do not know R naught value, because at 0 degree there is no mention of resistance. So equation is simple. Let us consider that at reference point, which is 0 degree centigrade, the R, the resistance is basically how much? R naught. Resistance is basically how much? R naught. Are you able to get me or not? So then, this implies that R at 50 degree I can define or not, which is equal to R naught 1 plus alpha, and delta t is simply 50 minus 0, which is 50. So this is given R at 50, which is 100. 100 is equal to R naught 1 plus alpha into 50. Are you able to get me or not? Then I can define R at 100 with respect to R naught or not, 0 degree centigrade. It will be R naught 1 plus 100 minus 0, which is 100. And this implies R at 100 I have to find, which is equal to, basically I can write the same equation, isn't it? Are you able to get me or not? So let us consider this as first equation, this as second equation. And can I divide first and second or not? So what I will get? 100 by R of 100 is equal to R naught 1 plus alpha into 50 divided by R naught 1 plus alpha into 100. R naught cancel. This implies I'll get the equation. Multiply this. 100 plus alpha into 1, 2, 3, 4, 10,000 is equal to R100 divided by 1 plus alpha, which is 2 into 10 to the power of minus 2 into 50. Are you able to get me or not? Is that clear? Are you able to get me? So look over here, what I will get as the lesson. This alpha is 100 plus 2 into 10 to the power of minus 2 into 100 into 100 divided by, this is 0, will cancel 1, and 5 2s are 10, so it will be cancelling 1. So 1 plus 1, which is equal to R. So R is equal to this 10 to the power of minus 2, this got cancelled. 200 plus 1, 100 is 300 divided by 2, which is equal to, so R at 100 degree centigrade is not 200, balki how much? 150 ohms. This is my correct answer. Got it? Hmm. Is that clear? May I ask you one more question? Question is very simple. Two resistors, one is having resistance R1 and thermal coefficient alpha 1, and another one is R2 and thermal coefficient alpha 2, are connected in series. Okay, with relays are connected in series. The question is find the relation. Find the relation for which equivalent resistance equivalent resistance does not change with temperature. Very logical question. Try to think. Do it. Okay. Try to do it. 1 minute. I'll take a break. बन गया. Should I help? Acha. Basically, these are two resistors which are connected in series, isn't it? So, can I just consider? Let's suppose these are given for 0 degree centigrade. इसके लिए दिया हुआ है. तो R equivalent at 0 degree centigrade will be what? Simply R1 plus R2, isn't it? Acha, what will happen at some another temperature? It will be R dash equivalent, and this one will change R dash, isn't it? R dash 1 plus at some random temperature T degree centigrade. Are you able to get me or not? So what is R dash 1? R dash equivalent is simply R1 1 plus alpha delta T or not, plus this R2 dash is R2 1 plus alpha delta T. Are you able to get me? Now R dash equivalent can be written as what? Simply R1 plus R2 plus R1 alpha 1. So there are alphas, different alphas, alpha 1 and alpha 2. So R1 alpha 1 plus R2 alpha 2. Change in temperature will be same, which is delta T. Are you able to get me or not? So basically, if this R dash equivalent does not want to depend on temperature, that means what? R1 alpha 1 plus R2 alpha 2 must be equal to 0 such that R dash equivalent does not depend on temperature, isn't it? So you got the relation that what is the relation? R1 alpha 1 plus R2 alpha 2 is equal to how much? 0. But in reality, what is the meaning of this? That R1 alpha 1 is equal to minus of R2 alpha 2 or not. So that means that one material I need to require a positive alpha. For another material, I require a negative. So that means positive is for which? Conductors. Negative is for which? Semiconductor. So the answer is very very simple. That one is conductor, means out of these two resistors, one is a conductor and another one must be a semiconductor. Any can be conductor, vice versa is also possible. हाँ, एक को कंडक्टर चाहिए, दूसरा सेमीकंडक्टर चाहिए, then only they must be connected in series. हाँ हाँ हाँ. Yes, that we make it in our batteries, in our homes, inverters. We add like this way only. one semiconductor, one resistor, such that if the temperature increases, then the balance of the circuit should be possible. Okay, and they try to make it that R1 alpha 1 must be equal to minus of R2 alpha 2. Yeah. Okay. Got it? Okay. Let us do once again same kind of question. All right. Find the equivalent thermal coefficient of resistivity which is denoted as alpha equivalent for following case. For following cases. First one is, let's suppose if I consider first one is when the resistors are connected in series. Okay, this is R1 alpha 1 and this is R2 alpha 2. Okay, second case is both are connected in parallel. Hold on. Second one is what? Both are connected in parallel. R1 alpha 1. Find the equivalent thermal coefficient in both cases. Is that clear? Do it fast. Tell me what will be the answer? Anyone? Anything done? Well, let us start. I've given you already how much minutes? 6 minutes. Okay, let us do it. Let us first go through our series connection. Okay. Okay. In the series, what I have R1 alpha 1, R2 alpha 2. First, I need to define my reference now. Consider R1 and R2 are present at 0 degree centigrade. Okay. Whatever it is given always, just consider them to be present at 0 degree centigrade. Yes. So, first one, R equivalent is R1 plus R2 at 0 degree centigrade. Are you able to get me or not? Then R dash equivalent will be R1 dash plus R2 dash at any random temperature T degree centigrade, isn't it? So R dash equivalent, what I can write? R dash equivalent will be simply R1 plus R2 because they are in series into 1 plus alpha equivalent into delta T or not. For R dash equivalent, I am saying. Got it? So R1 dash will be what? Simple R1, 1 plus alpha, 1 delta T. And R2 dash R2, 1 plus alpha 2 delta T. Is that clear or not? Got it? Because see, R equivalent, R dash equivalent will be written as, the reason for this is R dash equivalent is what? Nothing but R equivalent at 0 plus 1 plus alpha equivalent into delta T or not. But what is R equivalent as 0? R1 plus R2. Is that clear? So if I just put it, what I will get? R1 plus R2 plus R1 plus R2 into alpha equivalent delta T is equal to R1 plus R2 plus R1 alpha 1 plus R2 alpha 2 into delta T or not. So this and this got cancelled. Delta T got cancelled. and I got my alpha equivalent in series, which is exactly equal to R1 alpha 1 plus R2 alpha 2 divided by R1 plus R2. Got the answer? Is that clear? Let us do for our parallel connection in similar sense. For second one, parallel. In parallel, once again, same thing, let us consider. But here 1 by R equivalent I need to write now, which is 1 by R. Which one? Which one? Where? So in parallel connection, 1 by R equivalent is 1 by R1 plus 1 by R2, isn't it? In parallel connection, this is my R equivalent formula, na? At 0 degree centigrade. Now, at random temperature, it is R dash, R1 dash, R2 dash at T degree centigrade. Is that clear? So can I move ahead? So the equation will be what? Just use this equation. 1 by R equivalent is what? 1 by R equivalent into 1 plus alpha equivalent delta T, isn't it? Is equal to 1 by R1 is how much? R1 dash is R1 1 plus alpha 1 delta T plus 1 by R2 1 plus alpha 2 delta T. Is that clear or not? Are you able to get me? Now, this alpha equivalent into delta T are very, very small values. This alpha into delta T, as you know that, they are even less than 1 or not. So we will do the approximation now. Approximation. As we know that alpha into delta T is less than 1. So remember that 1 by any term 1 plus x, which is very, very small, is written as 1 minus x. Simple. Got it or not? Okay. If x is very small. So here alpha is very small. Na? So it will be like I'll do for 1 plus 1 bar alpha equivalent delta T is simply 1 minus alpha equivalent delta T. Is that clear? So the equation becomes what? Simple, the numerator becomes, okay, the numerator becomes 1 by R equivalent 1 minus alpha equivalent delta T is 1 by R1 1 minus alpha 1 delta T plus 1 by R2 1 minus alpha 2 delta T. Is that clear or not? Okay. So basically, what I can do? I can write this equation that is 1 by R equivalent. I can write it as what? 1 by R equivalent minus 1 by R equivalent alpha equivalent delta T, isn't it? Can be written as 1 by R1 plus 1 by R2 bracket close, and this is minus of alpha 1 by R1, isn't it? Plus alpha 2 by R2 into delta T. Can I write like this way or not? Isn't it? So this, once again, this and this got cancelled, isn't it? So minus minus will also cancel. And 1 by R equivalent is how much? Nothing but 1 by R1 plus 1 by R2 into alpha equivalent delta T is equal to delta T will also cancel, isn't it? delta T also got. So it is alpha by R1 plus alpha 2 by R. This is your answer. Are you able to get me or not? You can still convert it as you can see that, but I don't, I'm not left out with any space. I'll write it over here. So I have the equation 1 by R1. So I can take it as LCM R1 R2 R1 plus R2 into alpha equivalent is equal to alpha 1. If I take the LCM over here, it will be alpha 1 R2. R1 R2. So this got also got cancelled, and this implies that alpha equivalent in my parallel connection is alpha 1 R2 plus alpha 2 R1 divided by R1 plus R2. So you got one very good result actually, that if I consider the series connection, this, yeah, alpha equivalent is R1 alpha 1 plus R2 alpha 2 divided by R1 plus R2. But when I consider my parallel connection, this R1 alpha 2 plus R2 alpha 1 divided by R1 plus R2. This is one of the most important conclusion based on temperature. Is that clear or not? So your temperature dependence of resistance is over. Battery equations are left, connection of battery and all. I think one or two more classes I'll require, and after that I'll start capacitance, whatever is left out, and then we'll move to magnetic effect of current and all. Okay? Is this clear or not? ठीक है? So till this, the topic is totally finished.